Welcome back to another lesson in MCV4U. Today we'll be talking about continuity. Informally, a function is continuous if you can draw its graph without lifting your pencil. So example, if I draw a line here, it looks like this, and I don't stop, that would be considered continuous. If I have to stop, lift up my pencil, and then completely finish there, that would be considered not continuous. So the definition is a function y is equal to f of x is continuous at x is equal to a if the limit as x approaches a of f of x is equal to f of a. In other words, a function is continuous at x is equal to a if the following three conditions are met. Number one, f of a actually exists. So there's a corresponding y value for x is equal to a. The limit as x approaches to a of f of x exist. And finally, the third, f of a is equal to the limit as x approaches to a of f of x. So again here, the limit as x approaches a exist and equals f of a. So just a note here. So all polynomial functions, are continuous for x is an element of all real numbers. So if a function has holes or gaps, then it is discontinuous function or said to have a discontinuity. So there are three types of discontinuity that we'll look at. Number one is there is a point or removable discontinuity, and that's commonly seen as a hole. We see in here, there's a hole at x is equal to a. And again, the limit of x approaches a of f of x cannot equal f of a. So similar here, we see that there's a hole in this second example. So a function y is equal to f of x has a point or removable discontinuity at x is equal to a if the limit of x approaches a of f of x exists, but f of a is not defined, or if the limit as x approaches to a of f of x does not equal f of a. So two conditions can cause a point discontinuity. A jump discontinuity here is if a function y is equal to f of x has a jump discontinuity if x is equal to a, if the left side and the right side limits exist. So if the left side and right side limits exist at x is equal to a, but they are not equal to each other. So here we see that the limit as x approaches to a from the left of f of x did not equal the limit of x approaches a from the right of f of x. And we see that in the diagram here on the right-hand side. The third type of discontinuity is what is called an infinite discontinuity. So a function y is equal to f of x has an infinite discontinuity at x is equal to a if at least one of the left side or the right side limits is unbounded, which means that it approaches infinity or negative infinity. So here's a couple of examples of infinite discontinuity. So here's a couple of graphs that will show you infinite discontinuity. So here, again, these are all showing infinite discontinuities at x is equal to 0. So that should be a whole. So again, let's write that down. So these all showing infinite discontinuities at x is equal to 0. Okay, so let's look at this example number 1 here. It says the function f of x is represented graphically in the figure below. State whether y's f of x is continuous or discontinuous or discontinuous at the following x values and state the type of discontinuity if applicable. Okay, so let's look at x is equal to -3. So x is equal to -3. Here, if we go to the graph on the right, here we can see that there's particular y value. Again, there's also the few things that we're looking at. So remember, there's a corresponding y value. Again, the limit exists, which means that left hand and right side, and then the value is the same as f of x. So here we can indicate that it is continuous. For x is equal to -2, we see that there's a hole, and so here we can indicate that it's a point discontinuity. Third, at x is equal to 0, x is equal to 0, we see here that there's another point discontinuity. At x is equal to 3, as we see, it continues on, and so this would be infinite discontinuity. Okay, and then lastly, at x is equal to -1, we see here that there would be a jump discontinuity. Okay, so let's look at example 2 and let's look at some actual functions now. And so here it says determine the values of x where each function is discontinuous, and identify the types of discontinuity. So here we see that y is equal to x plus 4 over x minus 7. So here we understand that there's going to be a vertical asymptote at x is equal to 7, which means that there is going to be an infinite discontinuity at x is equal to 7. So here we write there is an infinite discontinuity at x is equal to 7. Okay, and then if we look at here, we have y is equal to x over 3x squared minus 6x. So again, we can factor out the denominator. And so here we'll have y is equal to x over 3x, x minus 2. x can cancel out. We'll be left with y is equal to 1 over 3 bracket x minus 2. Remember stating restrictions here, x cannot be equal to 0. And we also have a vertical asymptote at x is equal to 2. So therefore, we have few things. So here, number one, we have a vertical asymptote at x is equal to 2, which means that therefore we have an infinite discontinuity at x is equal to 2. And therefore, there's also a hole at x is equal to 0. Which means that there's therefore also a point discontinuity at x is equal to 0. Okay, so let's look at example number 3. So here again, it says state the set of x values where for each function is continuous. So again, state the set of x values for which each function is continuous. So here we look at our first value. Again, our first value here and is a polynomial, right? And we know that polynomials are continuous, as we noted in the note before. So this is a polynomial. Therefore, continuous for x is an element of all real numbers. And so x is continuous. Here is element from negative infinity to positive infinity. Okay, so here, if we look at this second question here, it has y is equal to square root 2x plus 1. So if we write our domain, we know here that 2x plus 1 has to be greater or equal to 0. So 2x is greater or equal to negative 1. X is greater or equal to negative 1 over 2. So here we can write a note. So a square root function is continuous for all x values in its domain. And therefore, here we see that it's continuous. See, it's continuous for here. X is an element of real numbers, and x has to be greater or equal than negative 1 over 2. Or we could also write here, we can write it as x is an element, real numbers from negative 1 over 2 to infinity. And remember, these square brackets can mean that it's included. Okay, so let's look at this third example here, or C. And so here it's y is equal to 1 over x cubed plus x squared minus 16x minus 16. So here we can factor out some values at the bottom. And here using factoring by grouping. So we get 1 over x squared bracket x plus 1 And here, if we factor out a -16, we'll also get x plus 1. And so now we have y is equal to 1 over x plus 1, x squared minus 16. You see that we have a difference of squares there. So if y is equal to 1 over x plus 1 and x plus 4, x minus 4. Here we have a couple of restrictions here again. So we have our vertical asymptote. X is equal to -1, x is equal to -4, and x is equal to +4. And therefore, it's continuous here for x is an element of real numbers, but it cannot be continuous at x cannot be equal to -1, -4, and 4. So that's where it's not continuous. Or you can also write it like this. X is an element from -infinity to -4, and from -4 to -1, and from -1, 4, and finally from 4 to infinity. So again, that u value just means the union. Okay, so let's look at example 4. So here, example 4, it says express as a piecewise function and sketch the graph. For what values of x is the function continuous? Okay, so a couple of things. So here, when x minus 3 is greater or equal to 0, so this is the positive, x is greater or equal to 3, so no change there. And then also, when x minus 3 is less than 0, x is less than 3, and so there, that's going to be that -1 value, or that's going to be the negative. Okay, so if we write our function in piecewise notation, a piecewise function, we can see that here, negative x minus 3, x minus 3, that's when x is less than 3. And we also have x minus 3, x minus 3, when x is greater than equal to 3. So here we can see that if we rewrite this, if f of x is equal to negative x minus 3 squared, x is less than 3, and x minus 3 squared for x is greater than equal to 3. Okay, so let's look at the limits from the left-hand and right-hand side. So the limit of f of x as x approaches 3 from the left is equal to negative 3 minus 3 squared, which is equal to 0. We look at the limit as x approaches 3 from the right of f of x. Here we see that's equal to 3 minus 3 squared, which is also equal to 0. Therefore, we see that the left-hand and the right-hand limit, the left-hand limit is equal to the right-hand limit. Okay, so again, it is a polynomial here. So polynomial. So what does that mean again? So each piece is continuous. Also, if we just sub in f of 3 into the equation, or the a value here, it's equal to 3 minus 3 squared, which is also equal to 0, which is good. So the limits and f of a are equal to each other. And so therefore, this continuous at x is equal to 3. So therefore, the function y is equal to f of x is continuous, for x is an element of real numbers. So therefore, let's just write that. And therefore, y is equal to f of x is continuous for x is an element of real numbers. Okay, and so if we draw our graph, so here if we draw our graph again, so at 3, and so here we'll go down, and oh look, something like that. So just wanted to clarify in terms of this graph as well. Again, I made it look like it was an open circle, should be a closed circle, again, because it's continuous as you go through. Okay, so let's look at example number 5. Here it says algebraically analyze. So what does it mean to algebraically analyze? So algebraically analyze means to use formal limit definitions. So algebraically analyze the continuity. So when we say continuity, that means, again, state we're continuous. So state we're continuous, state where it's discontinuous, so state we're discontinuous, and the type of discontinuity. Okay, so again, here we see that each piece, again, since it's a polynomial, so each piece is a polynomial. Which means that it is continuous for x is an element of real numbers. However, we do have to check if it's continuous at 2 points, at x is equal to 0 and x is equal to 1. So here we must check for continuity at x is equal to 0 and x is equal to 1. We do that by looking at the limits and subbing f of 0 into the equation. So here, let's start with at x is equal to 0. We see that the limit as x approaches 0 from the left of f of x, we're going to use the value here of x, and therefore that is equal to 0. And then secondly, the limit as x approaches 0 from the right of f of x, that's equal to the limit as x approaches 0 from the right of x squared, and that would be equal to 0 squared, which is equal to 0. So far, so good. Left-hand limit, right-hand limits are the same. Here we have f of 0 is equal to x squared. Sorry, is equal to f of 0 is equal to x squared, which is equal to 0 squared, which is again equal to 0. So again, f of a is equal to 0, and the limit from x approaching a is also 0. And therefore, we know that it's going to be continuous. So we can write that formally here. So the limit as x approaches 0 of f of x is equal to 0, and f of 0 is also equal to 0. Therefore, it is continuous at x is equal to 0. Okay, now let's look at it at x is equal to 1. So at x is equal to 1, here we have the limit as x approaches 1 from the left of f of x, which is equal to the limit as x approaches 1 from the left, which is x squared, which is equal to 1 squared, which is equal to 1. Okay, so for the left-hand limit, it's equal to 1. The limit as x approaches 1 from the right of f of x is equal to the limit here of x approaches 1 from the right of x squared plus 1. So that's going to be equal to 1 cubed plus 1, which is equal to 2. So here, the left-hand limit does not equal the right-hand limit. You can write that on the other side here. So the left-hand limit did equal the right-hand limit. Right. So therefore, we can write here, formally the limit as x approaches 1 negative of f of x, so from the left, does not equal the limit as x approaches 1 from the right of f of x, and therefore there's a jump discontinuity at x is equal to 1. And so therefore, we can write this whole thing as f of x is continuous for x is an element of real numbers, but cannot equal 1. And then there's a jump discontinuity at x is equal to 1. Okay, so let's look at this last one here. So it says, for example, 6, for what value of the constant c is the function f of x equals x plus c, x is less than 2, and cx squared plus 1, x is greater or equal to 2, continuous for x is an element of real numbers. So here, again, both pieces are polynomials. Which means that both pieces are polynomials, so continuous. Okay, so to be continuous, again, at x is equal to 2, then we have to look for the left-hand and right limit. So the limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the right of f of x. And therefore, we can set up a system of equations here. So here we have limit as x approaches 2 from the left, represented by the equation x plus c, is equal to the limit as x approaches 2 from the right is represented by the equation cx squared plus 1. And so here we have 2 plus c is equal to c 2 squared plus 1. 2 plus c is equal to 4c plus 1. Rearrange, get 2 minus 1 is equal to 4c minus c. Here we have 1 is equal to 3c, and therefore c is equal to 1 over 3. So therefore, the value of c, which makes this function continuous, is 1 over 3. Okay, and then one last thing we want to look at is this special case here. So when f of x is isolated from the function, as in the example of the right, and the function is only defined by one side of a, then this does not qualify as either point discontinuity or a jump discontinuity. Note here, the limit as x approaches a from the left of f of x does not equal the limit of x approaches a from the right of f of x.